Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
A team of quantum engineers at UNSW Sydney has developed a method to reset a quantum computer, that is, to prepare a quantum bit in the zero state, with very high confidence, as needed for reliable quantum computations. The method is surprisingly simple. It is related to the old concept of Maxwell's demon, an omniscient being that can separate a gas into hot and cold by watching the speed of the individual molecules. Here we used a much more modern demon, a fast digital voltmeter, to watch the temperature of an electron drawn at random from a warm pool of electrons. In doing so, we made it much colder than the pool it came from, and this corresponds to a high certainty of it being in the zero computational state, says Professor Andrea Morello of UNSW, who led the team. Quantum computers are only useful if they can reach the final result with very low probability of errors. And one can have near-perfect quantum operations, but if the calculation started from the wrong code, the final result will be wrong too. Our digital Maxwell's demon gives us a 20x improvement in how accurately we can set the start of the computation. The research was published in Physical Review X, a journal published by the American Physical Society. Watching an electron to make it colder. Professor Morello's team has pioneered the use of electron spins in silicon to encode and manipulate quantum information, and demonstrated record high fidelity, that is, very low probability of errors, in performing quantum operations. The last remaining hurdle for efficient quantum computations with electrons was the fidelity of preparing the electron in a known state as the starting point of the calculation. The normal way to prepare the quantum state of an electron is go to extremely low temperatures, close to absolute zero, and hope that the electrons all relax to the low-energy, zero, state, explains Dr. Mark Johnson, the lead experimental author on the paper. Unfortunately, even using the most powerful refrigerators, we still had a 20% chance of preparing the electron in the 1 state by mistake. That was not acceptable, we had to do better than that. Dr. Johnson, a UNSW graduate in electrical engineering, decided to use a very fast digital measurement instrument to watch the state of the electron, and use real-time decision-making processor within the instrument to decide whether to keep. The effect of this process was to reduce the probability of error from 20% to 1%. A new spin on an old idea. When we started writing up our results and thought about how best to explain them, we realized that what we had done was a modern twist on the old idea of the Maxwell's demon, Professor Morello says. The concept of Maxwell's demon dates back to 1867, when James Clerk Maxwell imagined a creature with the capacity to know the velocity of each individual molecule in a gas. He would take a box full of gas, with a dividing wall in the middle, and a door that can be opened and closed quickly. With his knowledge of each molecule's speed, the demon can open the door to let the slow, cold, molecules pile up on one side, and the fast, hot ones on the other. The demon was a thought experiment, to debate the possibility of violating the second law of thermodynamics, but of course no such demon ever existed, Professor Morello says. Now, using fast digital electronics, we have in some sense created one. We tasked him with the job of watching just one electron, and making sure it's as cold as it can be. Here, cold translates directly in it being in the zero state of the quantum computer we want to build and operate. The implications of this result are very important for the viability of quantum computers. Such a machine can be built with the ability to tolerate some errors, but only if they are sufficiently rare. The typical threshold for error tolerance is around 1%. This applies to all errors, including preparation, operation, and readout of the final result. This electronic version of a Maxwell's daemon allowed the UNSW team to reduce the preparation errors 20-fold, from 20% to 1%. Just by using a modern electronic instrument, with no additional complexity in the quantum hardware layer, we've been able to prepare our electron quantum bits within good enough accuracy to permit a reliable subsequent computation, Dr. Johnson says. This is an important result for the future of quantum computing. And it's quite peculiar that it also represents the embodiment of an idea from 150 years ago. Video. U2.be/YNRW61RXOM Mark A. I. Johnson, Mateusz T. Madzik, Fei E. Hudson, Kohei M. Ito, Alexander M. Jakob, David N. Jameson, Andrew Jorick, Andrea Morello. Beating the thermal limit of qubit initialization with a Bayesian Maxwell's daemon. Physical Review X, 2022, 12-4, doi, 10.1103, Phys Rev X. 12.041008 University of New South Wales. New quantum computing feat is a modern twist on a 150-year-old thought experiment. Science Daily, the 29th of November 2022. ift.tt/ltier1fh. University of New South Wales, 2022, November 29th. New quantum computing feat is a modern twist on a 150-year-old thought experiment. Science Daily. Retrieved November 30, 2022 from ift.tt/ltier1fh University of New South Wales. New quantum computing feat is a modern twist on a 150-year-old thought experiment. Science Daily. ift.tt/ltier1fh. Accessed November 30, 2022. Thanks for watching. Please subscribe my channel for more videos.